So, hello all, very good morning to all, and welcome to my class. Today, we are going to start our new chapter that is a chemical bonding, chemical and ionic equilibrium. Right. So, this chapter is very important in a point of advanced paper. So, we are trying to cover this entire chapter in our two class. Today is this is the first class of this chapter, and tomorrow we are going to solve some PYQ and some important concept from this chapter. Right. Today also we are going to do some numerical as well. So let's start with the today's session. Before this, I hope my voice is audible to you and my screen is visible to you all. Okay. So if you have any problem related to this, you can text me so that I can correct this. Right. Okay. So let's start with the today's session that is chemical and ionic equilibrium. What is basically this is? So as we see here, what is this? This actually represent the equilibrium state, right? So this basically represent the how the equilibrium state is achieved, right? So basically equilibrium is nothing but it is a stage at which the amount of reactant which get react to give product. So amount of reactant which reacted to give product is equal to amount of product that give back the back reactants, right? It means at the time of equilibrium, the concentration of both reactant and product may be same. Right. It means the rate at which the forward reaction occur is exactly equal to the rate at which the backward reaction occur. So the equilibrium point means where equilibrium is attained means the rate of formation of product become equal to rate formation of reactant, and this point is we known as equilibrium, right? So let's see this thing. First of all, what do you mean by this term equilibrium, right? So basically, on carrying any chemical reaction in a closed vessel at a particular temperature, initially the reactant concentration keep on decreasing, right? And the product concentration keep on increasing. So this is the basic behind the equilibrium. Okay, whenever the chemical reaction is started at a particular temperature, what happen is this: initially the reactant concentration keep on decreasing and product concentration keep on increasing. Now, after some time, a stage is reached at which there is no net reaction, and this stage is called state of equilibrium. So this stage we known as state of equilibrium. As we can see in the screen, that is A plus B, that is the reactant which react together to give C plus D, right? So here A plus B and C plus D are in equilibrium with each other, right? Because at equilibrium, the concentration of A plus B is exactly equal to the concentration of C and D. Now, when such a stage is achieved between the ions and undissociated electrolytes, it is termed as ionic equilibrium. So basically, we in this chapter we are going to study the two type of equilibrium. One is a chemical equilibrium, and another is a ionic equilibrium. So in ionic equilibrium, we basically study about the ions and undissociated electrolytes, right? Now, there are the two following types of equilibrium. The first one is equilibrium involving the physical process and the equilibrium involving the chemical process, right? So what do you mean by this equilibrium involving the physical process means in all the processes which attain equilibrium, two opposing processes are involved, right? So in all the processes which attain equilibrium, the two opposing processes are involved. If these opposing processes involve only physical changes, the equilibrium is called physical equilibrium, right? Commonly occurring physical equilibrium are as what are the examples of the commonly occurring physical equilibrium? So basically the solid liquid equilibrium, this is represent a dynamic equilibrium between the ice and water. So this is an example of solid liquid equilibrium, right? So this basically represents a dynamic equilibrium between ice and water. So this is H2 is in a ice form and this is H2 in liquid form. So here the rate of melting is exactly equal to the rate of freezing. So this is known as solid liquid equilibrium, or we can represent it as dynamic equilibrium, right? Now, what is liquid gas equilibrium? Basically, on heating a pure liquid, it start converting into its vapor, right? So when you heat a liquid, it start converting into the vapor. If the process is carried out in a closed vessel, the vapor get condensed again to given liquid, right? If the vapor is open, then this will convert into the vapor, and this will not get returned back, and they will not condense cells, right? So for condensation, it is must condition is you carry this whole process in a closed vessel, right? The vapor get condensed again to the given liquid. Now, after some time, a stage is reached at which the rate of evaporation become equal to the rate of condensation, right? And this point is known as liquid gas equilibrium. So at this stage, the volume of the liquid water and the vapor become constant. Such a stage represent liquid gas equilibrium, or we say H2O is in liquid form or H2 is in gas form, occur at 373 Kelvin, or we say 1 atmospheric pressure. So when we say that the liquid gas equilibrium achieve when the rate of evaporation, right, we can understand when the rate of evaporation become equal to rate of condensation, then we can say that liquid gas equilibrium will be achieved, right? Now remember one important note here: the temperature at which the pure liquid start to convert into the vapor is called boiling point. If someone asks what is boiling point, so you can say that the temperature at which the pure liquid start to convert into the vapor is called boiling point. At this temperature, the vapor pressure of the liquid become equal to the atmospheric pressure. That's why the boiling point changes with the change in altitude, right? So always remember this thing, the boiling point depends upon the pressure. So whenever there is a change in the pressure, there is also change in the boiling point. Okay, so at this temperature, the vapor pressure of the liquid become equal to the atmospheric pressure. So if in a hilly area or some any other place where the atmospheric pressure is less, then the boiling point is also less, right? So that's why the boiling point changes with the change in the altitude. So these 2 points are very important to learn. Try to remember this point. Now, what is solid vapor equilibrium? Can you understand this thing? Solid vapor equilibrium. Basically, such equilibrium which exists only in a case of sublimate, like that is a substance which on heating directly get vaporized without showing liquid state. Right. So if a sublimate like solid iodine is heated in a closed vessel, after some time, the vessel get filled up with the violet vapor and the intensity of the color increase with the time, right? So such such equilibrium exists only in the case of sublimates. Sublimates, always remember this word. Sublimates means the substance which can heating directly get vaporized without showing any liquid state. Right. For example, let's see the example behind this. What is the example? Yeah, this is an example. As we can see that this is the iodine vapor, right? So if the sublimate like solid iodine is heated in the closed vessel, solid iodine is heated in the closed vessel. After some time, the vessel gets filled up with the violet vapor and the intensity of the color increase with the time, right? So as the time goes on, the intensity also increases. So this we can show, this we can clearly see this, the example of solid vapor equilibrium, right? Now, after some time, the intensity of the color become constant. At this state, the rate of sublimation of solid become equal to the rate of condensation of the vapor into solid, right? Such a state is referred to the equilibrium state. So I2 is in solid form and I2 is in vapor form. They are equilibrium with each other. So how can you write that beta? That is rate of sublimation become rate of condensation. In the previous case, what we write, that is the rate of, yes, rate of vaporization is equal to rate of condensation, right? So there's the example of liquid into gas, or this is the example of solid into gas. So rate of sublimation is equal to rate of condensation. Now, what is the general characteristics of equilibrium involving physical process? So can you tell me the general characteristics of the equilibrium involving the physical processes? Basically, at equilibrium, the measurable properties of the system remain constant. Always remember this thing. At equilibrium, the measurable properties of the system always remain constant. Now, equilibrium is possible only in the closed system. Always remember this thing. Let's see the example. If you consider the example of the liquid and gas vaporization, then if you heat the liquid and if you not close the vessel, then obvious their vapor will be evolved, they are emitted out, right? So in this there is no formation of condensation, so condensation does not take place. Then how can you say that how the removed vapor can back converted into the liquid, right? So this is not possible in case of the open system. So whenever the closed system is there, then only equilibrium will take place. In the open system, we cannot have any type of equilibrium, right? So this is one of the most important and first condition for the equilibrium to be exist. Equilibrium is possible only in a closed system. The next one is also very important. Equilibrium is dynamic in nature. So what do you mean by this term dynamic in nature? Basically, dynamic means the opposing processes do not stop but takes place at the same rate, right? So equilibrium is dynamic in nature. That is, the opposing processes do not stop but takes place at the same rate. For example, sometimes you observe that okay, there is no change in the concentration of the reaction. So we can say that this attain the equilibrium, or this is static equilibrium in nature. There is no changing happening there. But no, this is not the true. The true is what? Because equilibrium is dynamic in nature. It means the rate at which the product formed is exactly equal to the rate at which the reactant formed. So you observe every time the amount of reactant, amount of the product remains the same. Why? Because the time in which the product react to give reactant is the same time in which reactant give back to product as well. So the amount of both seems to be like same. But what happening is they are continuously changing concentration, but we can't observe the change because they are dynamic in nature. It means the time in which the product give reactant is exactly the time in which the reactant give a product back, so that we can say that equilibrium is dynamic in nature. Okay, now the physical equilibrium is characterized by the constant value of one of its parameters that are given temperature. Now, for the dissolution of CO2 in water at equilibrium, we can say that CO2, which is in gas form, and if you want to dissolve in water, so CO2, aqueous upon CO2 gas is a constant at a given temperature. That there exists an expression involving concentration of the substances, right? This constant is called the equilibrium constant, and greater the value of equilibrium constant, greater is the extent to which CO2 dissolve in water, right? So this constant is called the equilibrium constant. I hope you understand this thing. Good, very good. Now, this one is very important question, basically from the chemical equilibrium part, right? So, what the question asks, beta? You have to answer this question. Read it carefully. Very. What the question asks? An open beaker of water in equilibrium with the water vapor is sealed container. When the few grams of glucose are added to the beaker of water, the rate at which the water molecule leave to the solution decreases, leave the solution increases, leave the vapor increases, or leave the vapor decreases. So you have to identify the following. Which one is correct out of this? Identify, beta. Yes, you all identify this thing. An open beaker of water in equilibrium, right? And you have to identify out of the following which one is correct, right? No one. So very interesting. No one will reply this. Okay. Let me explain it to you. देखो, an open beaker of water is an equilibrium with the water vapor in the sealed container, right? So एक open beaker है water का equilibrium के साथ, and एक है water vapor in the sealed container. When the few gram of glucose are added to the beaker of water, right, to the beaker of water which is open, the rate at which the water molecule, right, the rate at which the water molecule leaves the solution decrease, leaves the solution decrease, because whenever we add some solute, non-volatile solute to the solvent, right? Their vapor pressure start decreasing, because the vapor pressure of the pure liquid is if P naught. Then obviously, if you add some non-volatile solute like anything solid, their vapor pressure start decreasing. So an open beaker of water. So when the few gram of glucose are added to the beaker of water, the rate at which the water molecule leave to the solution start decreasing. So the correct option for this question is nothing but okay. Now, let's see the next one. That is equilibrium involving the chemical processes, right? So, if during a chemical reaction, the rate of a forward reaction become equal to the rate of backward reaction at a given temperature, pressure, and concentration, the reaction is said to be under the chemical equilibrium. So, when you say that chemical equilibrium we achieve, so now we come to the our topic for today, or the topic for this chapter, that is the chemical equilibrium. So if during a chemical reaction, the rate of the forward reaction become equal to the rate of backward reaction, and at a given temperature, pressure, and concentration, the reaction is said to be under the chemical equilibrium. Okay. Now, equilibrium involving a chemical processes. Basically, the reaction which proceed in both the direction and do not react to completion. Do not reach to completion, right? The reaction which proceed in both the direction and do not reach to completion are known as reversible reaction. It, it means reversible reaction is never 100% completed, right? Those reactions which are not 100% completed are said to be reversible reaction. Basically, in this reaction, which proceed in both the direction and do not reach to completion are known as reversible reaction. It is represented by putting a double-headed arrow like this, as we represent between the reactant and the product. One arrow pointing towards the product and the other pointing towards the reactant. So this is how we can actually represent the chemical equilibrium process, right? Now, some example of such reaction are as follows. For example, when the Fa react with H2O, the formation of Fe3O4 plus H2 takes place. So this two arrow represent one, above arrow represent the formation of Fe3O4 and the below arrow represent how Fe3O4 and H2 combine together to give back H2 and Fe. Right, similar for the case of HI. The reaction which moves in one direction only, the reactant are almost completely converted into product are called irreversible reaction. So always remember this thing, the reaction which move in only one direction, or we say the reactant are almost completely converted into product are called irreversible reaction. While the reversible reaction are those reaction which can take place from the each side, right? Now, some example of such reactions are, for example, BaCl2 and Na2SO4. So, this reaction is very, very fast reaction, precipitation reaction they are basically. So, this is an example of irreversible reaction. Similar decomposition reaction. A reversible reaction become irreversible if one of the product, for example, a gas is allowed to escape. Right. So, if irreversible process, if any irreversible process like 2 KClO3 plus KCl plus 3O2. So this is a irreversible reaction. Now, if you want to convert this in a reversible, then what you have to do is just allow this O2 gas to escape. So a reversible reaction become irreversible, right? If reversible reaction become irreversible, right? Understand this thing. This reversible reaction, the above two cases, right? This one and this one. So these two cases, that is a reversible reaction, become irreversible if one of the product, for example, a gas is allowed to escape. Now, what is the type of chemical equilibrium? So basically, if the equilibrium reaction contain only one phase, then that equilibrium is homogeneous, right? So if what we can actually classify the type of chemical equilibrium into two parts, that is homogeneous and heterogeneous. So if the equilibrium reactions contains only one phase, contain only one phase, then the equilibrium is homogeneous. Similar, if it's contain different phase, then that equilibrium is called heterogeneous, right? For example, H2I2 will give 2HI. So here you can observe that both H2I2 and 2HI are present in a gaseous form. So they are the homogeneous with only gaseous phase. MgCO3, so they are the heterogeneous with the solid and gaseous phase, because in this MgCO3 is in solid present, MgO which is in solid present, but CO2 is present in gas, right? So this is a heterogeneous with the solid and gaseous phases. Now, let's see this concept of a chemical equilibrium. What the concept behind the chemical equilibrium? So when the equilibrium is attained in a chemical reaction, all the observable properties of the system like concentration, color become constant. It appears that the reaction stop altogether at equilibrium, but this is not true. At equilibrium, the rate of forward reaction become equal to the rate of backward reaction. We already discussed this thing. This means there is no net change in the concentration of reactant or product. In other words, the equilibrium state is dynamic balance between the forward and the backward reaction. Now, at equilibrium state, through graph, we can understand the rate of forward reaction become equal to the rate of backward reaction. This can be seen in the graphical mode as well. So this is a graph between the time and the rate, right? Like rate of reaction and the time. So initially we can observe that as initial, the rate of forward reaction, that is the formation of product, is zero. So as the time goes on, rate of forward reaction become increases, right? Similarly, as the time goes on, rate of backward reaction also start, right? Let me explain with this example. Now, let us assume this is A plus B and this will C plus D, right? So initially, the product is zero and reactant is also supposed to be, maximum, right? So if I'm talking about in the terms of rate of forward reaction, so rate of forward reaction means what? Rate of forward reaction means this one, that is from A plus B to how C plus D produce. This is called rate of forward reaction. And this is rate of backward reaction, how from C plus D you will prepare A plus B. So at initial, both the rate of forward and rate of backward reaction are zero. When the time started, the rate of forward reaction start increasing. So this is the rate of forward reaction start decreasing, right? So this is the rate of forward reaction. This is start decreasing, right? This is the start of rate of forward reaction start decreasing. Similar on the basis of we can understand the rate of backward reaction. So rate of backward reaction start increasing because as the product start being forming, they can return back to the reactant side, right? They can return back to the reactant side. So at starting, the rate of forward reaction is maximum, right? Because concentration of reactant is good. As the time goes on, the rate of forward reaction start decreasing and rate of backward reaction start increasing. This point is achieved. This point is called equilibrium. So at this point, equilibrium is achieved where the rate of both the reaction, that is the rate of forward reaction and rate of backward reaction become equal. So this is known as equilibrium state. Further equilibrium of the reaction can be attained from both the sides. The equilibrium concentration of reactant and product will always be the same, whether we begin with the reactant or the product. The variation of the concentration of the reactant and product is reversible reaction and can be seen as. So from this graph also we can observe this. That is, this graph is for the variation of the concentration of the reactant and product, right, with the time. So equilibrium state is dynamic, not static in nature. Remember this. It means that the reaction does not stop, but both the opposing reaction are going on continuously with the same speed, right? So sometimes we can see that there is no change in the composition, there is no change up here. So it means they are a static in nature. But no, equilibrium are dynamic, not static, right? It means that the reaction does not stop, but both the opposing reactions are going on continuously with the same speed. So, what are the characteristics of chemical equilibrium? So, basically, in a chemical equilibrium at a given temperature, the measurable properties like pressure, concentration, density, or color remains constant, right? Basically, a chemical equilibrium can be attained from the either side. Chemical equilibrium can be attained in a lesser time by the use of catalyst. So, just remember this thing: catalyst increase the chemical equilibrium, right? So chemical equilibrium can be attained in the lesser time by use of the catalyst. However, catalyst does not change the chemical equilibrium as it affects the rate of both the forward and the reverse reaction to the same extent, right? So remember this, if someone asks, does any effect of catalyst on the chemical equilibrium? So you can say that no, catalyst does not change the chemical equilibrium because as it affects the rate of both forward reaction and reverse reaction to the same extent, right? So you can remember there. Now, chemical equilibrium is dynamic in nature means what? That the reaction does not stop but continue in both the direction with the same speed. The chemical equilibrium will continue indefinitely if the conditions such as the temperature and concentration are not changed. So the chemical equilibrium will be continue indefinitely if the conditions such as the temperature and concentration are not being changed. Now, this is a concept which question for you. This question was asked in the JEE Main 2020 as well. So sometime this type from related to this topic also the question will come in the advanced paper, right? So you have to identify the following which of the graph is the correct for this. Right. So the for the equilibrium from A to B, the variation of the rate of forward and the reverse reaction with the time is given by. So from the graph A, B, C, and D, which graph will be correct? A represent the rate of forward reaction and B represent the reaction with the reverse reaction, right? Which of the following graph is correct, beta? Can anyone? Can anyone explain me? No. Okay. So we already see this. That is first one. As we see that there is a decrease in the concentration of the forward reaction, and there is an increase in the rate of the backward reaction, right? So this is the graph we obtained, right? So this is the nothing but this graph, right? So at this, the rate of forward reaction will equal rate of the backward reaction. So this is absolutely correct. Now, what is law of mass action, or we say law of a chemical equilibrium? So this law is very important to understand because from now many numericals and many questions, KP, KC, they all we can calculate from this law only. So what is law of mass action, or we say law of chemical equilibrium? Basically, the rate at which the substance react is directly proportional to its active mass. And the rate at which the chemical reaction proceed is proportional to the product of the active masses of reacting species, with each concentration term raised to the power of the stoichiometric coefficient of that in a chemical reaction, right? So this is how we can actually represent. It means, what does it say? It say that when you have a plus b, c plus d, let us suppose a mole of a, b mole of b, c mole of c, and d mole of d are present. Then how will you write the law of mass action, law of a chemical equilibrium? So this is nothing but the chemical equilibrium constant comes out to be product concentration, reactant concentration upon this is CD, this is A, and this is A. Right. So this is how you can actually calculate Kc. You understand this thing? What is law of mass action? Good. Now, the term active masses means the molar concentration. That is the number of moles per liter. So many of you having no problem related to this. So what is this active mass? Active mass is called. So active mass is nothing but active masses means the molar concentration. That is the number of moles per liter, right? So you have to calculate the number of moles per liter. This is the actual thing. Now, it is expressed by enclosing the formula of the substance in a square bracket. So always remember this thing. It is expressed by enclosing the formula of the substance in the square bracket. So always you represent active masses, that is a molar concentration, right? That is the number of moles per liter in like this. Thus, the active masses of H2 can be represented as H2. Okay. Remember this. Active masses of pure solid and liquid are taken as unity because their concentration or density remains same throughout the reaction. Right. So the active masses of pure solid and liquid are taken as unity because their concentration or density remains same throughout the reaction. Now, how will you derive the expression for the equilibrium constant? Can anyone? Let me derive so that you can understand this thing in a easy way, right? So let's see how will you derive the equation, that is AA plus BB, and this will gives us CC plus DD. Okay. So how will you derive? According to the law of mass action, according to law of mass action, according to law of mass action, rate of forward reaction is directly proportional to the concentration of the reactant, that is A into B, right? This is the according to the law of mass action. Similar, where proportionally constant, if you remove the proportionally constant, it is equal to Kf. So Kf, A raised to the power A, B raised to the power B. This is equation 1. Similar, the rate of backward reaction is nothing but it is equal to Kb into concentration of C raised to the power C, D raised to the power D. So this is about the second one. Okay. So where Kf and Kb are the rate constant for the forward and backward reaction. Now at equilibrium, we know that rate of forward reaction is equal to rate of backward reaction. At equilibrium, rate of forward reaction becomes equal to rate of backward reaction. So we can write as this is nothing but Kf, concentration of A raised to the power A, B raised to the power B, is equal to Kb, C raised to the power C, and D raised to the power D. So we can derive as Kf upon Kb. What does Kf upon Kb come? Kf upon Kb is nothing but this is Kf upon Kb. So this will comes Cc, right? So this is Kf upon Kb comes out to be concentration of the product, right? Divided by the concentration of the reactants like AA and BP, right? And this Kf upon Kb is known as K. So this is the expression for the equilibrium constant Kc. So how will you actually find the value of Kc? So you can find the value of Kc like this only, right? That is Kc is equal to Kf upon Kb, or we say Cc, Dd, Aa or Bb, right? So this is how you can actually find the value of Kc. Okay, so this is the expression for the equilibrium constant from the law of mass action. I hope it is clear to you. Good. Similar. This equation is also called a law of chemical equilibrium where Kc is equal to Kf about Kb constant and it is known as the equilibrium constant. It has a definite value for every chemical reaction at a particular temperature regardless of the concentration of the reactant. Now, if Kc is expressed in terms of mole fraction, it is denoted by Kx, right? So if the Kc is expressed in the terms of mole fraction, it is denoted by Kx. So how will you represent Kx? Kx is nothing but the mole fraction of Cc, XDD, XAA, and XBB. So simple. Just in place of the concentration, we use the mole fraction. In terms of partial pressure, we can also represent equilibrium constant like Pc raised to the power C. Rest all are same, just in place of concentration and mole fraction, we just put pressure, that is the vapor pressure, right? So the law of chemical equilibrium may be stated as at a given temperature, the ratio of the product of the equilibrium constant of the product to that of the reactant, each raised to the power equal to their respective stoichiometric coefficient in the balanced chemical equation has a constant value. Right. So let's see the one example so that you can easily understand this thing. So in this question, what they ask basically, so in this question, they are asking about how you can actually calculate. So nitric acid oxide react with Br2 and give nitrosyl bromide as per the reaction given below. 2NO plus Br2 give 2NO Br. When 0.087 mole of NO, 0.0437 mole of Br2 are mixed in the closed container at a constant temperature, 0.0518 mole of NOBr is obtained at equilibrium. The equilibrium amount of NO and Br2 are respectively. So you have to calculate the equilibrium amount of both NO and Br2. So let me explain this thing. Okay, so let's see what the reaction is. That is 2NO plus Br2. This will gives us 2NO Br, right? So 2NO plus Br2, this will gives us 2NO Br. So what is the initial mole? Initial mole, right? So initial moles is nothing but is equal to, if I'm considering about NO, initial moles are given 0.0, just wait, 0.087, right? Similar, initial mole of Br2 is also given. 0.0437, and this is the product, so we know that this value is 0, right? So this is 0, right, at starting. Now, at equilibrium, what happened? So at equilibrium, let us assume that if 2NO is equal to 2NO, right? So if the 2 mole of NO will react with the 1 mole of Br. So if let us assume if 0.087, if the 2 mole is dissociated 2x, then in this case it is in two cases 2x, in the cases x will be dissociated, right? So this will be equal to 0.0437 minus x. This x is the dissociation, right? And here also it is equal to 2x. Okay, so at equilibrium this will be happening. Now, we know that if you comparing with the given information, the value of NOBR at equilibrium is already given. So we are to mix in a closed container at a constant temperature. 0.051 mole of NOBR is obtained at equilibrium. So just compare this thing NOBR. So by question itself, that is from question. From question itself, it is given that what is given that beta, that is the number of moles of NOBR, that is 2x is equal to 0.0518. So how will you calculate x? X will you calculate as 0.0518 divided by 2. So it comes out to be how much? That is 0.0259. Right. So this is the value of x you calculated. Nothing but 0.0259. So this is the value of x. So you know the x. Then how you calculate NO and BR? So you can calculate as, for example, NO, the concentration of NO become, the concentration of NO is nothing but 0.087 minus 2x. So it will become 2 into 0.0259. So on subtracting, you'll get this is equal to 0.0352 mole, right? 0.0352 mole. Similar, the concentration of, how will you represent the concentration of Br2? So Br2 is calculated as, it is nothing but 0.0437 minus 0.0259. So we'll get the concentration of BO2 as 0.0178 mole. Okay, so I hope this is clear to you. So which one is the correct answer for this question, beta? Because in this question they are asked, you have to calculate the equilibrium amount of NO and Br2. So NO we having 0.0352 and 0.0178. So correct option is A, right? So the correct option for this question is A. I hope you understand this question. Anyone having any kind of doubt, you can ask. No doubt, right? So let's see, there is a certain relationship between Kp and Kc, right? So what is the relationship between Kp, Kc and Kx? So these three are very important. Kp is known as equilibrium constant at in terms of pressure, in terms of concentration, in terms of mole fraction. So they are the equilibrium constant. So we know that if you consider a general phase equation like N1A, N2B, and this will give M1C plus M2D and so on. So according to the law of mass action, you will write Kp is nothing but pressure in terms of pressure. That is the Pc and their stoichiometric coefficient PD, Pa and Pp. Now in terms of molar concentration, we can write C, concentration of C raised to the power M1, concentration of D raised to the power M2, A, B and so on. We know that PV is equal to nothing but nRT. This is from the ideal gas equation. We know PV is equal to nRT. What is P here? N upon VRT. N upon V is also known as concentration. So this is equal to CRT. Now put the value. PA becomes CART, PB becomes CBRT, PC becomes CCRT, PD becomes CDRT. Just put the value. When you put the value, what you will get beta, that is Kp is equal to this much RT into delta Ng. What is this delta Ng? This delta Ng basically they are the power like M1, M2, N1, N2, right? So this Kp, this is the relationship, very, very important relationship will derive. So if any question or anyone asks what is the relationship between Kp and Kc, when Kp and Kc become equal, anything related to this, just remember Kp is equal to Kcrt raised to the power delta Ng. Where how will you calculate delta Ng beta? For example, if the reaction like H2 plus I2, this will gives us 2Hi, right? This is in gaseous form. 1 mole of H2 and 1 mole of I2 combined together to form 2Hi, right? So how will you calculate delta Ng? This is in gaseous form. This is also in gaseous. So delta N of gases is nothing but the all the summation of product side minus my reactant side. So product side, how many gas? Only we have a 2Hi. So number of mole is 2. Now the left hand side, 1 mole of H2, 1 mole of I2. This is also 2. So this is 2 minus 2 is equal to 0. So for such case, delta Ng is equal to 0. So if the delta Ng is equal to 0, then in this case, Kp is equal to Kc. Right? Just remember this thing. So when the delta Ng is equal to 0, so in any question, first of all, you have to calculate delta Ng and try to understand what the value of delta Ng is. If the delta Ng is 1, then obvious Kp is greater than Kc because Kp is something into Kc, right? And if the delta Ng is equal to 0, then Kp is equal to Kc. Okay, so this is the important reaction. Now, we also know that in terms of mole fraction, how will you arrange this? We know that this is a pressure. This pressure is nothing but mole fraction into a total pressure, right? We know the formula that is a partial pressure is equal to mole fraction into total pressure, right? That is a partial fraction is equal to Pt, total fraction into mole fraction. So this formula we know. So just put the formula in this. What we will get, that is Kp is equal to Kxp delta Ng. Kp is equal to Kcrt delta Ng. Kp is equal to Kxrt delta Ng. So this is what we get in terms of Kp, Kx, and Kc. So this first one, this is the this one. This is the relationship between Kp and Kx. This is relationship between Kp and Kc, and this is relation between Kp and Kx. Right, Kp and Kx. Right. So this is how we can actually derive this. So if Ng is 0, then Kp is equal to Kc. If Ng is positive, then Kp is greater than Kc. If Ng is negative, then Kc is greater than Kp. So this important conclusion you must remember, right? So that you can easily understand this thing and solve this question in a next time. Now, this question is also very important. This is also JEE Mains question, right? So what the question basically asks, so in this question, they are asking to you about what is the relationship, right? You have to know, calculate the relationship. If the equilibrium constant of A, B, and C is K1 equilibrium, and that of B plus C is equal to P is K2 equilibrium, a constant for. So you have to calculate the equilibrium constant. What is the K1 upon A for A to P? You have to calculate the equilibrium constant for A to P. We have a two equation like when A and B gives us B plus C. Similar for another one is when the B plus C gives us P, right? B plus C gives us P. So when the A gives us B plus C, their equilibrium constant is nothing but K equilibrium, K1, right? So the equilibrium constant is given in this case K1, or we represent as K1 equilibrium. Similar for this, it is given that is K equilibrium, that is 2. Okay, so the equilibrium constant for this, that is A to P in terms of K1 and K2. So how will you calculate with the equilibrium constant from A to P? Let me say first normal thing, that is how what is the equilibrium constant for this. So that is K equilibrium is nothing but this is equal to concentration of P upon E, right? This is how we can calculate now. Similar, K equilibrium 1 is what? K equilibrium 1 is what? That is concentration of B, concentration of C upon concentration of A. Similar, K equilibrium 2 is nothing but concentration of P, concentration of B into concentration of C, right? So, what is this K equilibrium 3? So, how will you obtain P by A? So, this is nothing but P and this is by A. So, just if you multiply this thing, right? P into B plus C multiply by this one, right? So if you multiply K equilibrium 1 with the K equilibrium 2, what you will get? K equilibrium 1 is nothing but concentration of B, concentration of C, concentration of A. Multiply concentration of B, concentration of B, concentration of C. They are cancelled out and you'll get P by A. This is the desired equation we want now, P by A. So this is equal to K equilibrium into K equilibrium 2. So just multiply this. So what is the correct action for this? That is option number C. Right? So this is the correct answer for this question. I hope this is clear to you. Good. Now, what is the characteristics of equilibrium constant? So you have to identify the characteristics of equilibrium constant. So what are the characteristics of equilibrium constant, beta? The value of equilibrium constant does not depend on first, that is the initial concentration of the reactant, the presence of catalyst, the direction from which the equilibrium has been attained. If the equation is divided by the factor n, the new equilibrium constant is the nth root of the previous value. We are going to see some important formula related to this. What happened when you divide the equation? What happened when you reverse the equation? And all this thing. The important note here: the value of equilibrium constant is independent of initial concentration of the reactant, the presence of a catalyst, and the direction from which the equilibrium has been attained. Now, if the equation is divided by the factor n, the new equilibrium constant is the nth root of the previous value. Like, if the equation is multiplied by the factor n, the new equilibrium constant is the nth power of the previous value. That is, for example, for this reaction, that is half N2 plus 3 by 2 H2, this will give us n is 3, right? So here the Kc is given 1 by 5. Therefore, the reaction, if you multiply this equation by 2, you will get N2 plus 3 H2 is equal to 2 N is 3. The new Kc dash is equal to square of the Kc, that is 1 by 5 square. This comes out to be 0.04. Now, similar, if the equation represents the equilibrium constant is reversed, the new equilibrium constant is inverse of the first value. For example, Kc is given 6.3 into 10 raised to the power 14 at 1000 Kelvin for this reaction, NO plus O3, this will give NO2 plus O2. So Kc is this and this will give. For the reverse reaction, that is NO2 plus O2, and this will give NO plus O3. So Kc dash is equal to this. From equation 1 and 2, we can say that Kc dash is equal to 1 upon Kc. So 1 upon 6.3 into 10 to the power 14 is equal to 1.587 into 10 raised to the power minus 15. So this is how you can actually derive. Got it? Good. Now, if two equations are added, their equilibrium constants are multiplied, right? So if the two equations are added, their equilibrium constants are multiplied. If they are subtracted, their equilibrium constants are divided. Always remember, equilibrium constants are never added or subtracted, right? So if they are subtracted, their equilibrium constants are divided. Always remember, equilibrium constants are never added or subtracted. Okay, always remember this thing. The value of equilibrium constant change with the change of temperature as what, like log K2 by log K1 or is equal to delta H upon 2.303 or 1 upon T1 minus 1 upon T2, where K1 is the equilibrium constant at the absolute temperature T1, K2 is the equilibrium constant at the absolute temperature T2, and delta H is the heat of reaction at the constant pressure, right? So let's see the first case through which we understand this formula in more detail. Like if delta H is equal to 0, neither heat is absorbed or nor evolved. Then log K2 minus log K1 is equal to 0, or we say K2 become equal to K1. I hope this is clear to you. Thus, equilibrium constant remains same at all the temperature if the delta H is equal to 0. Now, in case of case 2, if the delta H is greater than 0, the reaction is endothermic. Always remember, we know this thing, when the enthalpy is greater than 0, then the reaction is endothermic. Let T2 is greater than T1, then 1 upon T2 minus T1 is less than 0. So we can say that log K2 minus log K1 is greater than 0, or we say K2 is greater than K1. So always remember, when the delta H is greater than 0, or we say for the endothermic process, K2 is greater than K1. Hence the value of the equilibrium constant rise with the rise in temperature. So that we can say that the value of the equilibrium constant K1, K2, that will be rise with rise in temperature. Case 3, if delta H is less than 0, that is the reaction is exothermic. Let T2 is greater than T1, then log K2 minus log K1 is less than 0, or we say K2, K1 is greater than K2. Therefore, the value of equilibrium constant is lowered with rise in temperature. So just remember these three cases, right? That is case 1, when the delta H is 0, when the delta H is greater than 0, when the delta H is less than 0. Now, what is unit of Kc and Kp? So if the number of moles of reactant and products are equal, that is Mg is equal to 0, then Kp as well as Kc have no unit. So it totally depends upon the number of moles of the reactant and product, right? So if the number of moles of reactant and product are equal, that is delta Mg is equal to 0, in this case, the Kp and Kc have a no unit. If the reaction proceed with the increase in the number of moles, that is when the delta N is greater than 0, for example, PCl5, PCl3 and Cl2. As we can see here now, there the number of moles is more. How? You'll calculate delta N. So we can calculate delta N like, in product side we have a 1 and 2, 2 moles, and reactant side only 1 mole. So this is 1, right? So in this, the delta N is greater than 0. So whenever the delta N is greater than 0, like in the second case also 2 minus 1, 1, right? With the increase in the number of moles, then unit of Kp, that is atmospheric delta Ng, and unit of Kc is mole per liter delta Ng. Always remember. Then the unit of Kp is become atmospheric delta Ng, and unit of Kc is become mole per liter delta Ng. Right? If the reaction shows a decrease in the number of moles, that is delta Ng is less than 0, the N2 plus 3H2. Here in product side we have a 2 mole of NH3, right? So we can calculate delta N as 2 minus 4, that is minus 2, right? So if there is a decrease, so if the reaction shows the decrease in the number of moles, then Kp is calculated at atmospheric delta Ng, right? And the case is liter per mole delta Ng. Same as that, whenever the increase or decrease, just remember the value in case of negative or decreasing, the value is negative, or in case of increasing, the value become positive. Now, what is the significance of equilibrium constant Kc and Kp? So basically, greater the value of equilibrium constant, greater will be the tendency of the reaction to go in the forward direction. Remember. So greater the value of equilibrium constant, greater will be tendency of the reactant to go in the forward direction. Similar, greater the equilibrium constant of a reaction, greater will be stability of the product and unstability of the reactant. If the value of K is greater than 10 raised to the power 3, always remember the product predominate. So whenever the value of K is greater than 10 to the power 3, then products predominate. If the value of K is less than 10 to the power minus 3, then the reactant predominate. And if it lie between 10 raised to the power 3 to 10 raised to the power minus 3, considerable amount of both is present. Right. So from the value of a K, we get an idea about which predominates in a reaction. Right. So basically, just remember this value. The value is, if the value is greater than 10 raised to the power 3, the product predominates, obvious. If the value of K is less than 10 raised to the power 3, then the reactant predominates. Okay. And if it is in between 10 raised to the power 3 to 10 raised to the power minus 3, considerable amount of both is present. Next. Oh, this is very important, and this is totally a formula based question, right? So in this question, they are asking for the reaction, you have to identify the relation between Kp and Kc, right? So what is the relationship between Kp and Kc? We know that Kp is equal to Kc RT raised to the power delta Ng. Here, what is Kc? Kc is nothing but Kp upon RT, and this is delta Ng. Right. Okay. So this is Kp. Can you calculate delta Ng for this reaction? Delta Ng, what it comes? This is in solid form, not taken, taken, taken. So it will equal to 1 minus 3 by 2. Minus 1 by 2. Or we can say that Kc is equal to Kp, right? And this is RT ki power 1 by 2, right? So this is Kc. So Kc is equal to Kp, RT ki power 1 by 2. That is option C. Option C is absolutely correct. I hope you understand this question, how it come. Good. Next, reaction quotient or the mass action ratio. This one is very important. That is the reaction quotient, because the relationship between the reaction quotient and equilibrium constants were generally coming in the exam question, basically, right? So what is this reaction quotient, or we say mass action ratio? Basically, reaction quotient, is the ratio of the molar concentration or a partial pressure of the product species to that of reactant species at any stage in the reaction. Okay. So it is the ratio of the molar concentration or partial pressure of the product species to that of reactant species at any stage in the reaction. Now, for a reaction, A plus B gives us C plus D. Q is nothing but C, concentration of C into concentration of D divided by concentration of A into concentration of B. So reaction quotient Q is denoted as QC and QP. Depending upon whether the concentration is taken in terms of mole per liter or partial pressure respectively. With the help of reaction quotient, we can predict the direction of the reaction. So this one is the most important application of this. With the value of reaction quotient, we can easily, predict the direction of the reaction. How? Let's see. When Q is equal to K, right? When Q is equal to K, the reaction is in equilibrium. So whenever the value of equilibrium constant and the reaction quotient become equal. So when the Q is equal to K, the reaction is in equilibrium. Similarly, if the Q is greater than K, if Q is greater than K, the reaction moves from right to left, right? From right to left, that is backward reaction. So whenever the value of Q is greater than K, the reaction moves from right to left, or we say backward direction. If K having more value than Q, right? So if the value of K is more than Q, the reaction moves from the left to right, that is in forward direction, right? So this is how we can actually represent the reaction quotient, and this is the way in which the reaction quotient is related to the equilibrium constant, right? So just remember once more time, that is if Q is equal to A, Q is equal to K, then the reaction is in equilibrium. When the Q is greater than K, then the reaction moves from right to left, or we say it proceed towards the backward direction. When the Q is less than K, and that is the reaction move from left to right, and it is in forward direction. So I hope this is clear to you, right? Good. So this is a small question related to this. You have to identify this, right? So what you have to identify, Vita? You have to identify the a mixture of 1.57 mole of N2, 1.92 mole of hydrogen, and 8.13 mole of NH3 is reduced in the 20-liter concentration at 500 Kelvin. At this temperature, the equilibrium constant Kc for the reaction, the true statement is the reaction is at equilibrium, the reaction goes in the direction of product, and so on. So you have to identify this. So for this question, Kc is already given, right? So let me solve this. So for this reaction, Kc is already given. Kc is nothing but 1.7 10 raised to the power 2. This is already given. Now you have to calculate the reaction quotient, which is the calculation very much similar to the equilibrium constant, like NH3 raised to the power 2, and only product side is NH3 raised to the power 2 divided by N2 and 3H2. Sorry, only H2 power 3. Okay, good. So we know the concent. How will you calculate the concentration beta? Because we know the mole. So concentration of NH3, right? So let me calculate the concentration of each and every one. Like concentration of NH3, that is mole per liter. So mole is 1.5. For NH3, 8.31 mole. So 8.13 mole divided by 20 liter. So this is the concentration of NH3. Similar concentration of N2 is nothing but 1.57 divided by 20. Similar concentration of hydrogen, right? Concentration of hydrogen. So concentration of hydrogen is also 1.92. So this is equal to 1.92 divided by 20. So this is how you can find the concentration of each. Just put the value in this. So for NH3, we have 8.13, 20 raised to the power 2. For N2, we have a 1.57 upon 20. And this one raised to the power 1. Okay. And this one, that is O. It will comes out to be 1.92 upon 20. Any raised to the power, that is 3. Okay. So just solve this value. On solving, you'll get, because 2020 get cancelled. So what you left is Q comes out to be in this question. On solving, what you'll get, Q is nothing but equal to 2.379, 10 raised to the power, right? So this is the value of Q. Now let me tell Q and Kc, which one is more in this question? Kc की वैल्यू कितनी थी 1.7, 10 raised to the power 2. Q की कितनी आ गई 10 raised to the power 3. Obvious Q is greater than K. So if the Q is greater than K, what happens? Reaction will proceed in a forward direction, backward direction, or what? So obvious backward direction, that is the reaction goes in the direction of reactant. Backward direction means also reactant, right? So the reaction goes in the direction of the reactant side. So option 2 is absolutely correct. Now, this play a very, very, very important role, that is Lee-Chatelier principle. Okay, so what is Lee-Chatelier principle basically? So Lee-Chatelier principle state that when the change is brought about on a system is in equilibrium, the system tends to adjust itself to reduce the effect of change, right? So according to the Lee-Chatelier principle, when the change is brought about on a system in equilibrium, the system tends to adjust itself to reduce the effect of the change. Or we say, if the system in an equilibrium is subjected to a change of concentration, pressure, or temperature, the equilibrium shift in the direction that tends to undo the effect of the change, right? So this is how we understand the Lee-Chatelier principle. Basically, it states that when the equilibrium is attained, we have to do something to disturb this equilibrium so that only the reaction will take place. Otherwise, at the point of equilibrium, the reaction becomes stuck, or we say it does not bring the more product and all. So equilibrium, Lee-Chatelier principle basically comes to disturb the equilibrium and state that whenever the change is brought about on a system in equilibrium, the system tends to itself to reduce the effect of change. It means जब भी तुम इसको चेंज करोगे, जब भी तुम चाहोगे कि अच्छा इसके स्टेट को चेंज करें, तो अपने इक्विलिब्रियम को मेंटेन करने के लिए तुम्हें अपोज करेगा. ठीक है. So this is all about the Lee-Chatelier principle. Yeah, if for example, if you increase the concentration of the reactant, then equilibrium always want to increase the concentration of the reactant. And for this what happening, that is more and more product will be giving back a reactant. Similar, if you want to increase the concentration of the reactant, equilibrium will shift in a direction where they wants to decrease the concentration of the reactant. And by what they decrease the concentration of the reactant? By moving forward, because when the more product will be formed, then the reactant automatically get decreases. So this is all about the Leach-Atelier principle. So basically, the three factors that we are going to understand under the Leach-Atelier principle is concentration, right, and the temperature and the volume. Okay, so these three things we are going to study under the factors affecting equilibrium or Leach-Atelier principle. The first one is change in concentration. So if concentration of the reactant is increased or product is removed, the equilibrium will shift in the forward direction. Again, I repeat, if the concentration of the reactant is increased, let us assume if the concentration of reactant increase, then equilibrium wants to decrease the concentration because equilibrium always oppose, so that more and more product will be for this, right? So basically, if the concentration of the reactant is increased or product is removed, the equilibrium will shift in the forward. On the other hand, if the concentration of the product is increased, the equilibrium will shift in the backward direction. So these two possibilities are present. Now, change in pressure. So what do you mean by this term, change in pressure? The increase of pressure on a chemical equilibrium shifts it in that direction in which the number of gaseous molecule decreases and vice versa. Let me show with an example. Right. For example, this is PCl5. This will dissociate into PCl3 plus Cl2 gas. So these all are in gaseous. Now, so increase of the pressure. So in which side number of moles will be more? Obvious, product side we have a 2 mole, and reactant side we have only 1 mole, right? So whenever the increase in the pressure, so whether a increase in a pressure or decrease in a pressure is a good condition for this particular reaction. So when you increase the pressure, equilibrium shift in a direction where they wants to, you know, they want to decrease the pressure. That is in the side which having the less number of, right? So for such question, let us assume if you want to increase the pressure, then pressure increase means if you want to increase the pressure, give the pressure, then equilibrium will shift in direction where pressure is low, where pressure is low. So in which case pressure is low, where number of moles is low. So if you increase the pressure for this reaction, the equilibrium will shift in the direction where the pressure is low, like reactant side where the number of moles is also low. It means backward reaction is favorable by increasing the pressure. So if the pressure is increased, then the reaction is backward. Similar, if the pressure is decreased, if the pressure is decreased, then equilibrium will shift in direction whether they want to increase the pressure or we say that is the product side. So this is the desirable condition. So this thing you must remember and this thing you must calculate how this actually comes. Now, if Ng is greater than 0, there is no effect on the equilibrium due to the pressure change. If Ng is greater than 0, then there is an increase in the pressure and this will favor backward reaction. We already discussed this, right? If you increase the pressure, then equilibrium shift with whether the pressure is low or we say number of mole is low or we say this is in a backward direction. If Ng is less than 0, then increasing the pressure favor the forward direction. So always remember this all calculated on the basis of Ng. Okay. So low pressure favor the reaction where there is an increase in the total number of moles product, right? So the low pressure favor the reaction where there is an increase in the total number of moles of the product, and high pressure favor those where decrease in the number of moles product takes place. Next thing is temperature. So when the temperature is raised, the equilibrium is shifted in the direction in which heat is absorbed, right? So whenever the temperature is raised, whenever we increase the temperature is raised, the equilibrium is shifted in the direction in which heat is absorbed, right? Always remember. Thus, for the exothermic reaction, the increase in the temperature favors backward reaction, right? And for an endothermic reaction, the forward reaction is favored by the increase in temperature. because when the temperature is raised, the equilibrium is shifted in the direction in which the heat is absorbed, right? Just remember this thing. Uh, because as we see that, let me explain with an example again. And 2 plus 3H2 through Haber process, it will give us 2H. And some amount of heat is also released, which is a negative heat. Now, for such, what is the favorable conditions in terms of pressure and temperature? Can anyone tell? For this reaction, what is the favorable condition in terms of pressure and temperature? देखो, here the number of moles is 1 and 3, 4, and product side only 2. So the number of mole in the reacted side is more. So if we increase the pressure, then the equilibrium will be shifted in direction where the pressure is low, or we say it in forward direction. So if we increase the pressure, equilibrium shift in forward direction, right? So if you increase the pressure, equilibrium will be shifted in the forward direction because their number of moles is less, and this is the desired product. Similar, similar. This is already exothermic, but it means heat is already evolved. So heat is already evolved. So heat is already evolved. So for such process, you need less temperature. So the process in which heat is already removed, that is exothermic, we always require less temperature, right? And the process in which heat is required, the heat is not hot, it is very cold. Then the heat is required. So this is all about the change in temperature. Now, the next one is effect of catalyst. What is the effect of catalyst basically? So catalyst increase or decrease the forward and backward reaction equally. Therefore, equilibrium will be attained in less or no more time. So only the time required to reach the equilibrium state is changed by the presence of catalyst, right? So only the time required to reach the equilibrium state is changed by the catalyst. Thus, a catalyst does not affect the equilibrium constant. Also, catalyst does not appear in the balanced chemical equation as well. Now, the last one is what is the effect of addition of inert gas? So, if we keeping pressure of the system constant and an inert gas is added, it will increase the volume of the system. So, if keeping pressure of the system constant and inert gas is added, it will increase the volume of the system. Therefore, the equilibrium will be shifted in the direction in which there is increase in the number of moles of the gas. Right? So, therefore, the equilibrium will shift in the direction in which there is increase in the number of moles. If keeping volume of the system constant and inert gas is added, the relative molar concentration of the substance will not change. Hence, the equilibrium position of the reactions remain unaffected. Right? So this is the small chart which carrying all the important information of the Lee-Chatelier principle. That is the any chemical equation like AABB gives us CCDT and delta Ng is here. So concentration of A and B increase. So if you increase the concentration of A and B, then the equilibrium move towards the right. The equilibrium constant, no change. Any other points, no change. Similarly, if the concentration of C and D is increased, then the reactor move from the right to left, no change, no change. Pressure increase. So if the C plus D is if the number of moles of A plus B is greater than the C plus D, delta Ng become negative. So if the delta Ng is negative, right, then pressure increase case, and if the delta Ng is positive, and delta Ng is 0. So no change, very little effect. Similar temperature increase. To left, if delta H is negative, is exothermic, and if this is one is endothermic. So according to this, you can select. Now, addition of inert gas at constant pressure to the direction of the increasing gases model, no effect at constant volume also. Right. So this is how you can actually understand this thing. Now, what is application of Lee-Chatelier principle in industrial process? Right. So there are several applications we already discussed so far. The first one is Haber process. So basically, why we need Haber process? Haber process is used for the preparation of ammonia. Now, when the N2 react with the 3H2, the formation of 2NH3 and delta H is equal to minus 22.4 kilocalories form. The favorable condition are, first of all, high concentration of N2 or H2. That is the concentration of N2 and H2 are very high. High pressure, that is delta Ng is equal to minus 2. Low temperature as the reaction is exothermic. We already discussed this thing now. In this some reaction is released, that is the exothermic reaction. So we require low temperature and high pressure and high concentration of N2 or H2S. All through the low temperature favor the formation of NH3, yet optimum temperature is 500 degrees Celsius and pressure of 2 atm. So 2 atm pressure and the temperature of 500 degrees Celsius is necessarily required. Now, similar for the manufacturing of nitric acid. So basically, N2 combine with O2 to form 2NO, and this 2NO combine with the H2O to give the nitric acid. So the factors involving the formation of NO are, that is increase in the concentration of N2 and O2, unaffected by the pressure change, that is delta Ng is equal to 0, and increase in the temperature as the reaction is endothermic, right? For example, similar in the case of melting of ice, in above case, forward change is accompanied with the absorption of heat and decrease in volume. Hence, on applying Le Chatelier's principle, the favorable condition for the melting of ice are high temperature, right? As the forward reaction is endothermic, and high pressure. So at a high temperature and at a high pressure, as the forward reaction, so decrease in the water. Okay. Similar boiling of water, like water having a low volume is boiled under the stream having a higher. So let the forward changes accompanied with the adoption of heat and increase in volume. Hence, according to the Le Chatelier's principle, the favorable condition for the vaporization of water are high temperature and low pressure. So always remember this thing. The favorable condition for the boiling water is high temperature and low pressure. Solubility of the salt. If the solubility of the salt is accompanied by the absorption of heat, that is considered the solution of NaCl in water, the following equilibrium exists. Like whenever the NaCl is reacted with H2, it will form NaCl aqueous when the delta H is greater than 0. As the dissolution of NaCl proceed with the absorption of the heat, it is favored by the high temperature. If solubility of the salt is accompanied by the evolution of heat, that is KOS dissolved in the water with evolution of the heat, the solubility KOS thus decrease with the increase in the temperature. So in case of solubility of the salt also, they play a very important role. Right. So this is all about the chemical equilibrium. So we will cover all the important points of chemical equilibrium in today class. And from tomorrow, that is from tomorrow, we are trying to cover the ionic equilibrium part in detail, right? So that and some numerical as well. So we already covered today all the chemical equilibrium part, all important topics related to this chemical equilibrium, right? So all topics are already completed related to this ionic chemical equilibrium part. So sorry, chemical equilibrium part. So from next class, that is from tomorrow, we are going to start that is ionic equilibrium. So let's discuss some important things in case of ionic electrolytic, right? Ionic equilibrium basically. So what is this electrolytes and non-electrolytes, right? Can anyone understand this thing? What is electrolytes and non-electrolytes? Anyone? No one? Chalo, let me explain. What is electrolytes? Basically, the solute which dissociate into ions when dissolved in water and conduct electricity are called electrolytes. Basically, those solutes which dissociate into ions when they dissolve in water and conduct electricity as well are called electrolytes, right? So, however, not all the electrolytes ionize to the same extent in the solution. Some ionize very much and some ionize up to certain level only. Depending upon the extent of ionization, the electrolytes are divided into the two classes, the strong electrolyte and the weak electrolyte. Basically, the strong electrolyte, these are dissociated largely or almost completely in the solution, due to which the solution constantly become very good conductor of electricity, like HCl, H2SO4, HNO3, NaOH, KOH, NaCl, they all are the example of strong electrolytes. Similar on the basis of what are the example of weak electrolytes? So these get never completely dissociated. Like in ordinary condition, weak electrolyte dissociate in a solution to a small extent, and the solution consequently is a poor conductor of electricity, like CH3COH, H3PO4, H3PO3, ammonium hydroxide, ammonium carbonate, SCN. So these all are the example of weak electrolyte, right? And the similar basis, how we define non-electrolyte, a solution like urea, glucose, etc. does not contain any ion. Hence, the solution is a bad conductor of electricity. Such solution are termed as non-electrolyte, right? So, if anyone asks what is the difference between the electrolytes and non-electrolytes, you can give this answer to them, right? For example, electrolyte basically the solid which dissociate into ions when dissolved in water, and they also conduct electricity as well, right? And however, all are not 100% ionized. Maybe they ionize 100% as well, and maybe they not, right? So depending upon the extent of ionization, the electrolytes are further classified into the two types, strong and weak. So strong electrolytes are those which completely ionize, and the weak electrolytes are those which cannot completely ionize, right? So this is the example of all these things. On the similar basis, someone asked what is non-electrolyte. So basically, a solution of solute like urea, glucose does not contain any ion. Hence, the solution is a bad conductor of electricity, and such solute are termed as non-electrolyte. So I hope this is clear to you, right? So in today class, we are discussing all these things. So just revise this all so that you can able to solve some more numericals related to this topic, right? So in tomorrow class, we are going to discuss some PYQ question of the this chapter, that is ionic equilibrium and chemical equilibrium, and try to cover this ionic part as well. Okay, so let's meet in the next class where we'll discuss all these things.